Hello, everybody. We're going to talk about how to get excitation tables from characteristic tables. Now, the reason why we have each characteristic tables are used to do analysis. So imagine you already have a circuit and you want to find out, what is the actual underlying design of this? What does the state table look like? You know, basically, how does this all work? Um, then you know what the inputs J and K are when you're walking through, because on the circuit, you can start on the kind of left-hand side of the circuit and just calculate the values through. You eventually hit the individual registers, so you would know, depending on what the register type is, whether it's a JK, you would know what J and K are, and you want to know what the next state is, or you'd know what D is, and you want to know the next state, or you'd know what the value T coming in is, and you want to know again what is the next state of that going to be, so you can fill out the table. Um, so a characteristic table is used for analysis. That's what we've used so far. We're able to do it by looking at the design. How did we build those? Now we want to be able to use these to build something. So if we go from being analyzing the existing circuit to designing a circuit, excitation tables are used to design a circuit to achieve some other end. And in those cases, you already know what, for instance, the state table would be for your design, which means you know what the current QT is, and you know what the next QT is, and you have to figure out what J and K are, or you have to figure out D, or you have to figure out T. So because of that, excitation tables are used to. So, you know, I've written out what the excitation tables are here, but we want to talk about how do we get them and, you know, look at it from that standpoint. And then we'll do an example. So let's consider how to get the first one. We're going to walk row by row through here. So first off, we're going to take a look at the JK excitation table. So hopefully you can see my mouse here. Um, but if not, all I'm doing is kind of circling over the JK excitation table. So it's right hand, upper right hand table here. You can see we've got QT to QT plus 1, and we've got all the combos. QT starts at 0 and goes to 0. Starts at 0, goes to 1, 1 to 0, 1 to 1. Let's take a look at the first one, 0 to 0. Now, if I'm going from 0 to 0, I could just hold my value, which would be J0, K0 as my options. But since my final answer is a 0, I could also just reset things. A reset just makes the next state 0. It doesn't matter what the current state is. And that's a J0, K1. So since either hold or reset as a function would work, both of those have j equals 0, and it doesn't matter what the k value is, because I could either get hold or reset, and either one would work. So the k value doesn't matter. So as long as j is equal to 0, I will get this transition that I want. So that's how the first table comes from, because there's two different ways to force my next state to be 0. Keep the current qt, which is 0, or make the next qt 0, which is a reset. Two ways, away we go. So no matter what happens here, we're always going to have two options, and that's why we're always going to have an X on any row. And that gives us a lot of flexibility in our design. Take a look at the next line of this. We've got qt is equal to 0, and qt plus 1 is 1. So that means I could either flip current qt to get qt equals 1, or I could set it to be a 1, in which case it wouldn't matter what the current thing is. I'm just saying, hey, set it, make it 1. But the previous state doesn't matter. So I could either do a set or a flip. All right. Well, now, whichever one of these I do, j is equal to 1. So you can see that j is equal to 1 in the excitation table for the 0, 1 row. And k, it doesn't matter. If k is equal to 0, it sets the bit. If k is equal to 1, it flips the bit, but it's flipping a 0 into a 1. Either case, I end up with what I want. If I'm going from a 1 to a 0, I could either do a flip or I could do a reset. Reset will get me a 0 at the last state. A flip will turn the 1 of the current state into a 0 that I want in the next state. So I could do a reset or a flip to go from 1 to 0. And um, reset and flip both have k is equal to 1, but they differ on j. So j could be either 0 or 1 to get either reset or flip since both work. So I end up with x1 under jk. So you can see j is equal to x, k is equal to 1. On the line qt is currently 1, goes to qt plus 1 is 0. For the final row of the excitation table, I'm going from qt1 to qt plus 1 being 1. And so that means I could either hold or I could set the bit, right? Hold because the qt value and qt plus 1 are the same. So I just hold it to the next time instant, or I just set qt plus 1 to 1. Both of those have k is equal to 0. If you look inside the um, what's on the characteristic table, you look at set and you look at hold and you go, both k's are 0. Um, it's only j that differs between the two. So we say x. I don't care which one of those I get. I don't care if I'm holding. I don't care if I'm setting, as long as I end up with my value. Now, the easiest of the excitation tables to get, so that gives you JK. The easiest one is to do a D flip-flop. And that's because the D flip-flop only can do set or reset. So there's only one option, and it doesn't matter what the previous state is. So basically, you just say, what do you want? Put that value on the input. So it's a really easy table. We often don't even write this one out because, you know, you want a 0, put in a 0. You want a 1, put in a 1. This is your basic memory option. So the excitation table for a D flip-flop is trivial. Um, the last one I'm going to do is a T flip-flop. You'll notice I'm not doing the SR flip-flops because SR flip-flops essentially are just the upper part of a JK. It just doesn't have the flip option, but it does have the option to go bad on you. So we don't like that. We want safety. This is a basic digital logic design. If you go advanced digital logic design, we will like SR flip-flops again because we want speed. But then we have to be careful. So, but right now we're all about safety for the first course. So, safety wins and away we're gonna go. You notice for the T flip-flop, even though it only takes two of the options out of the JK table again, right? Hold and flip, the outside two. Um, but it needs four lines to express because both hold and flip depend on what the previous bit was. So that means I have to list the previous state bit and the next state bit that I want. So I end up with four options again under the excitation table, just like I did under the JKs, not because of the number of it's not the number of features that generate this, because remember the number of features here actually help me to, under JK, help me to get the X's in the table. Um, the number of rows in the excitation table depends on whether you're looking at just the next state or you have to look at both. T, you have to look at both. So you're going to end up with four. So I have the options of either hold or flip. And so there won't be any X's in here, but you'll notice the pattern, right? The JK flip-flops, if you look at it, ignore the X's for a second, you get this 0, 1, 1, 0 pattern going from J jogging over to K. Um, but if you look through those, you see that kind of pattern. We're going to have that exact pattern here. And it'll make sense why that's popping out. But basically you'll see that same pattern. So it's a good way to kind of remember the excitation tables is you should see this kind of like XOR like pattern. The T flip-flop has the XOR pattern, and the JK kind of has this split XOR pattern. The first half under J and the second half under K. and the rest of them are all X's. So it's a nice way to remember it quickly. Um, but anyway, for the T flip-flop, the outer two, going from a 0, staying a 0, or going from a 1, staying to a 1. So the first row and the last row of the excitation table. I just want to do a hold, right? Because that's the only way to get it. If I've currently got a 0, I want to go to a 0, I have to hold it. No other option. If you currently have a 1, you want to go to a 1, no other option. You must hold it. So therefore, we've got our basic coverage here on that. Okay, so given that situation, we can now take it and say, great, I want to hold. A hold means t equals 0. So the first and the last row of the excitation table, the value of t must be 0. When I've currently got a 0 and I want to go to a 1, or I currently have a 1 and I want to go to 0, the middle two values of the excitation table, the only way to do that with the T flip-flop is to do a flipping operation, which is T is equal to 1. So we get T equals 1 on the excitation tables. So this gives you the basic overview of how the tables are made, a little commentary on why they're there. Hopefully it makes some sense on how you're doing it. I'll do an example of this in another video just to keep the links of these to reasonable, and also so I have time to get all the graphics up here. But you now have a coverage of where excitation tables come from, and you know why. If you want to do a design, you want an excitation table. If you want to do an analysis, you want a characteristic table. All right, well, have a good day. Hope this helps you out.